All right. All right. So everyone can see my screen.
Yes.
Okay, great. So this is based on chapter 6, as we just went through in second edition of hands-on machine learning. This is a short chapter. It's like Ted was mentioning, the next chapter is on ensemble learning and random forests, and this is sort of a precursor. You can't have a forest without the trees. So this one's about the trees. I have some experience from classroom learning, classes I took on decision trees. I found that this chapter was very different. It assumes you have some experience or some knowledge and then goes a little deeper into the algorithm, which I guess is the purpose of much of this book, is to look under the hood. I did find the structure of the chapter itself, for the way my brain works, a little funky, so I may have changed it around a bit. For those of you who read it, you'll see what I mean. So first, what is a decision tree and what are its advantages and disadvantages? Well, very, very simply, a decision tree is takes a set of data, partitions it into nodes where you make very simple decisions throughout the nodes to get down to the different leaves. And then you can use it to classify or data or to predict values. And it has some advantages that we'll talk about here and some disadvantages that are covered throughout the chapter and illustrated, and we'll get into those a little bit. Some that are addressed by ensemble learning and random forests. So first advantage is that they're simple to understand and interpret. They're what's known as a white box model as opposed to a black box model. You can very easily see what is going on. They require very little data preparation. So for instance, if you worked with nearest neighbors, you may have to scale the data. Otherwise you get some funky results. There's no such need in a decision tree. They're versatile, as I mentioned. You can do classification and regression. I frankly don't even know what this next one truly means. So if somebody has a good intuitive description, but the cost of using the tree is logarithmic in the number of data points used to train the tree. I gather what that's saying is that they're pretty fast, but somebody could elaborate on that one.
Yeah. So when we were talking about support vector machines, there was some discussion about they're kind of slow. So if you have a lot of data, then it could take hours or longer to train one. So this one is actually fairly fast compared to a support vector machine.
Right. Okay.
Can I add one thing on that? So, question for Ted, maybe. Do we think that scaling is logarithmic in terms of training or in terms of inference later on?
What it says there is talking about inference time. Is related to the height of the tree, the depth of the tree, and that's usually logarithmic. But I guess I wasn't really reading it carefully. But that they are a lot faster to train than support vector machines too.
I think that I'd have to look closer at the book, but I think that the focus there is on inference because it scales much faster on inference actually, because you took in all of this data and then you capture it in a certain number of splits and you add more data, but it doesn't necessarily slow things down. Even if you have extremely complicated data, it still eventually will get more splits over time. But it will slow down after a certain point. If you have 1 million data points and then you go to 2 million data points, your tree isn't going to be 2 times as complicated because it will already have captured some of the information probably. So at inference, it won't be twice as slow necessarily.
Yeah, that's a great point. And I mean, if any of you guys, wind up working for like internet e-commerce companies, this is a significant issue, right? So they often have somewhere in the vicinity of 100 milliseconds to do all of their data analysis between the time you click and make a request and when they want to serve up the next web page to you. So like if you do a search on Wayfair for couches or something like that, they allocate somewhere around 100 milliseconds to the data science team. So how expensive in terms of time your inference is very important. You may have a slightly better model, but if it takes twice as long, you ultimately might not use it because you just don't have the budget.
Very good. Continuing with the advantages, can handle multi-output problems. You can validate results using statistical tests. I think chi-squared is definitely mentioned here in the book. And even if your assumptions are somewhat violated, the model can perform pretty well. As for disadvantages, I think the biggest one is that they're prone to overfitting, and I've got a slide later with, well, we could just jump to what that looks like. Well, maybe I didn't include it. There you go. So if you put no restrictions on your tree, you get many nodes. I think this keeps going below the picture, and this was from some exercise I did for a class, and it had 780 nodes or something like that. Anyway, so we'll get to pruning regulation later. The model can be unstable. We'll talk about this later as well, that basically that small variations can produce big changes. And predictions are, here's another one that is a bit over my head, but the predictions are piecewise constant approximations, not smooth or continuous. I gather that means something like a picture I'll get to later, but if you picture a smooth curve, that's not how your predictions come out. They come out in
stairs. Yes.
Yeah.
It looks like stairs on a plot.
Yeah, I don't know if you can actually see me or just the presentation, but I'm kind of drawing the stairs. And decision tree learners create biased trees if some classes dominate. And then here's the one that just made my head explode, because it sent me down a rabbit hole of looking up NP complete and all kinds of mathematical things that are well beyond my pay grade. But practical decision tree algorithms cannot guarantee to return the globally optimal decision tree, because learning an optimal decision tree is NP complete. And as a layperson, this boils down to me that I guess sometimes it'll find the local optima and won't find the global optimal decision tree. I mean, there's heuristics or shortcuts taken because of some as of yet unsolved mathematical problem. But somebody please clean up what I just said.
It means that quite often we just need a good enough model. We don't need the very best one. Ryan told about it, I think, a couple of meetings back, that in practice, you do not need Kaggle level decisions.
Yeah, what you said is right, Glenn. So the way trees are built, it uses a heuristic. It's a greedy heuristic. So at every step, it says, hey, with the points that I have remaining, what's the best way I can split them in half? And such that the left side and the right side are the most different looking, okay? And so, if you have a classroom of kids and you're splitting them, then maybe, you split based on boys versus girls, and then you split based on height, and then you split based on, color of their hair or whatever. But maybe if instead of doing it in that order, the first thing you had done was split based on shoe size, even though shoe size, it wouldn't immediately help you, it would have down the road made it much, much easier for you to, classify your data, right? There's no way to know that, all those what if questions. And so what they're saying is NP complete. It's more than polynomial time. It's exponential time to consider all those what ifs, right? So instead, what they do is they build what Maya said. They build a pretty good tree, but it's not guaranteed to be the best possible tree.
Very good. Yeah. And often we're not sending people to the moon, right? We're just trying to get more clicks on a page or sell more shampoo or whatever it might be.
Serve that page up, like Ted said, in a whatever the budget was, 100 milliseconds or whatever the budget they gave. That if you go over that, people click away and then you don't have a job anymore.
Right. So I guess my sort of takeaway from this last point was, don't be disheartened if you don't understand what NP complete means. Maybe it just doesn't matter. And I often hear Ted say things about the math being beyond his comprehension, which really humbles me, but also encourages me. So a note on computational complexity. Again, as somebody who's not a programmer by background, and I haven't dealt practically with these types of projects, this is a bit abstract to me, but the takeaway is that, as we've already covered, predictions are done very quickly, even on very large training sets. And what the algorithm, as Ted says, it's greedy algorithm, but it'll go back down and compare all the available features on all samples at each node, and then go on and on down the nodes. The little asterisk here is just say that you can set the maximum features, in which case, it will, the algorithm will only compare that many features unless it cannot find a partition, in which case it will exceed your number of maximum features. I don't know if this matters to anyone, as a practical matter, but to me, this was a bit of the going under the hood that I'm not accustomed to, and thought I should definitely mention it. And then, of course, you can estimate, as they have you do in one of the exercises, the time it would take to run a model if you had so many training instances. If you knew, say, like this number of training instances took an hour, well, let's say you had 10x those training instances, how long would it take? And that's where your big O notation comes in. But the bottom line is that they're very fast, and I gather that's why they're so powerful and so widely used, or at least they are the root of what is widely used, random forests. And then finally, even if you do, you can even speed them up more by pre-sorting the data. That's possible for, when you have smaller data sets, say, of less than a few thousand instances. But again, I'm just the facilitator. I'd like to open this up to comment if anyone would like to add. No?
I think this is good. If people understand this, it's great. If you don't completely understand how long it takes to run, I think it's, the key point is just, it's pretty reasonable in training time, and it's quite fast at inference time. So that's good enough if you don't know all the math.
Very good. Well, you've seen this one already, but I think actually,
by the way, Glenn,
Yeah.
So you're not in presentation mode. So if you could either, there was a comment in the chat, if you could either close the ribbon at top that just has all of the little menu options, or else go into presentation mode, just so we can see it bigger.
Is that better?
Yeah, except it's doing that weird thing where we have like, we see the next slidey thing, so you have to turn that off.
If you have multiple monitors, are you presenting on the other monitor?
Yeah, no, I've got multiple monitors. I've got you guys up on the other monitor. Do I
Okay.
need to shut off the other monitor?
Well, I don't know. It looks like this is presenter view.
Yeah, maybe under that display
Here.
settings at the
Yeah,
top. I
you
can't remember. There's a way you can turn
You
this off.
select
Is that
the
any
display
better?
settings.
There you
yeah,
go.
I got it.
Yeah, that's it.
I just disconnected my other monitor. So
Well, that's one way to do it.
this works fine. I didn't, this is actually better. I just, okay. So we were on this slide. Yeah. So before, I was going to get into like the comparison of we're going to get into the specific CART algorithm comparison of classifiers and regressors. But before that, this was one of those things where to me, things felt a little out of order. I think you have to understand impurity and talk about impurity and entropy before you get into that, but maybe not. Anyway, I think, here's the math, here's the formulas. This kind of stuff to me is always like presented. It's more complicated. It's less complicated than it seems, but it's very precise. Again, my preamble, I apologized already to all you mathematicians. But the idea with impurity, I mean, I'll just take it right out of the book. A node is pure if all the training instances it applies to belong to the same class. So if you get to a node and every training instance, when you go down to that node, you've got a sample size of whatever 100, and all 100 belong to the same class. That is an absolutely pure node, and therefore they measure it as impurity. The impurity score or index is 0 for that. So that's Gini impurity. Entropy, I won't try to tackle. It's a similar measure. I think what you see, the book talks about measuring also the change in entropy between nodes, and so that is also known as information gain. If you decrease the entropy between points. Again, this is the math, and then I gather that some algorithms use, well, actually, I think I looked at the documentation, and you can use entropy for a decision tree for CART, but the default is Gini, so it's one of the parameters that you could set. But then entropy is definitely, information gain is used in, say, ID3, which is, again, something I know nothing about, but seem to encounter in my reading and preparation for this presentation. And if anybody wants to comment on ID3 later on, maybe after we go through CART a bit, that'd be great. All right.
I can make a comment here really quickly. In terms of Scikit-Learn and CART, like you mentioned, they use these two, but in general, there are numerous impurity measures, and different types of decision trees may use different impurity techniques for how they control the splits or select the attributes. But in general, most researchers have pointed out that the splitting criteria doesn't really matter as much. And there was actually a paper that was written a while ago called like the theoretical comparison between the Gini index and the information gain. And so there were several models to kind of compare how drastically different using one or the other was. And they only found that it was a 2% difference. So 98% of it was exactly the same. And so for this session this week, like I decided to deploy decision tree model in Python. And so when I deployed one model using Genie and another model using information gain, I actually did achieve the same predictive accuracy results. So that further validates some of the previous research that was done, that it's very small between the two, and it's kind of an either or. But if you choose to use the Genie, it does compute the algorithm faster than the entropy method.
Thank you for that comment. You reminded me that I'm doing a disservice to the author, who does mention that it kind of doesn't matter. I would be curious, though, to flip this on its head, and if anybody who has a lot of experience with machine learning has encountered an instance in which one was superior to the other, that'd be interesting to hear about.
My experience with these is there's actually a decent number of different parameters that you can change. And this is not one of them that I would typically fiddle with. So it's important to understand in terms of what the algorithm is doing, but I would say that this isn't one of the parameters that you necessarily sit there and try a whole bunch of options on. There's different things that I think we'll talk about later that are more important in terms of performance impact.
Excellent.
I can mention that entropy measures, it measures on an interval and measures how far our points are from the mean value on this interval, if it is helpful. It is a rather interesting formula which allows to do this. So we want it to be small, which means that we want to be the values for our values for the outcome to be as flat as possible.
Okay.
Yeah, I'll just add to that to make it even simpler. So if people are new and they don't know the math, both of these will sort of measure randomness to a certain extent, okay? And so the opposite of randomness would be purity. So in the simple case where you're building a decision tree, let's say for a binary classifier, you're classifying cats versus dogs, okay? If you've got a data set and it's got 100 examples in it, and you find a variable that can perfectly separate all the cats from all the dogs out of those 100, then that's going to be the best split, you know. And so if you say, well, I can try splitting, you know, this by different features that I have. You have 10 different features, then it's going to evaluate at each step of the algorithm. It's going to evaluate all 10 of your features and say, well, what kind of split do I get? And for one of them, it'll say I split it 1090. Another one I split it 2080. Another one it doesn't split well at all, you know. And so the best split is the one that's going to give you the most only cats on one side and the most only dogs on the other side. And so then the question is like, well, if I have, you know, 43 cats and 2 dogs versus, you know, whatever on this side versus another one I have, you know, 53 dogs and 3 cats. Well, which of those is better? They're pretty close. And that's where you would use these formulas to tie break to say, So anyone that's like doing a terrible job and it's 20 cats and 20 dogs on the left and 30 cats and 30 dogs on the right, that you're never going to pick that as your split. You want something that's separating the cats from the dogs. And so this is just the fine details on exactly how would you tie break things that are pretty good at splitting, but just, you know, which one would you give the edges and say is slightly better?
All right. Well, I'm getting from this that I've spent too much time on this slide because it's not that important. So, but it is important, as someone mentioned, to understanding how the algorithm works.
Yeah, no, it is good. It's good. It's good discussion.
So speaking of the CART algorithm, which is you know, the basis of this chapter, the Scikit-Learn algorithm. You know, we've already talked about this, how it starts to work. It splits the training set into 2 subsets using a single feature and a threshold. And then, you know, how it chooses that is the greedy the greedy nature of the algorithm that we discuss. So difference between classification and regression, just a quick, I mean, I gather most people know this stuff, but you know, classification, you're predicting a class in each node of the tree. Gosh, I should probably show a tree. I mean, just to make sure we're level set here, but this is what we're talking about, nodes. And anywho, so a classification tree will predict a class, a regression tree will predict a value. I believe it's, if I remember correctly, it's gonna be an average value of the samples in that node. Is that right?
That's the vanilla tree algorithm. So
Okay,
when
yeah.
you're done building the tree, if you've got 10 examples when you get to the leaf, when you get to the end of the tree, then you're just going to predict whatever the average of those 10 is. That's the sort of vanilla tree algorithm.
Right. You could do it many other ways.
You can get fancier, yeah.
Yeah. And as we do, so we discussed impurity just now, and a classification tree in this case is going to try to minimize impurity. If you're classifying, as Ted said, you know, dogs and cats, you want to, it's not helpful to have a class that's sort of cat doggish, unless that's a new thing, the cat dog. But on a regression, because you're dealing with values, continuous data, you want to minimize mean squared error. And then the cost functions that the algorithm use are the same, except one is using impurity and one's using mean squared errors, as we can see here. So yeah, it's taking, for instance, if you want to just walk through one of these formulas down here, the way I understand this, so you're taking the sort of ratio of the instances on the left side to the total times the impurity level of that left side plus the same on the right. And then, you know, we're going to see left, right in a second here, but I imagine everyone can visualize a tree. Actually, we're going to take a break and look at irises. So this is what plants and flowers mean nothing to me. Again, I apologize to people who love this stuff, but I kept reading about it and it meant nothing to me. So I had to get a visual, and, you know, the iris data, this is what they're doing. And they're talking about petal width and petal length. And these are the three varieties, species that they're classifying. And although I didn't label them, you'll see later in the table, in the plots, that they've color coded the different classes, i.e. Setosa versus color. And oh, you know, I did this. I messed up. Sorry. This one I think is Virginica. Anyway.
As the guy from Virginia, I can't
I
believe
know,
you got Virginica wrong.
Did I get it wrong? Is it this one? Yeah. Say I'm not a flower person. I was moving them around to have them alphabetical. So then this one is Virginica. I'm going with that final answer. But yeah, anyway, that's what we're talking about here, unless we're talking about moons, but that was last chapter. Okay, so just visualizing classification. Again, we're talking about nodes and leaves, right? So here's a leaf, because you get down here and there's no children. And you can see in each of these, it'll produce the Gini impurity score, the number of samples, and then the values. So I forget what order it's in. It's probably not alphabetical, but you know, how many are in the different classes. I think that's what it's saying, yeah. So in this case, you know, the book goes through some simple code. I mean, I could hop over to the Jupyter notebook, but you could as easily go to the GitHub, to go to Get and just, you know, look at this yourself. But it's very simple code to produce this very simple tree where it's splitting on the petal length, and then, you know, deciding, well, if it's true that the petal length is less than 2.45 centimeters, well, that's all I need to know. That's setosa. But if you're going to tell me it's greater than 2.45, well, I need to, let me look at petal width. And if that's less than 1.75 centimeters, then, it's likely versicolor. And if it's greater than, then it's most likely virginica. And then you can see the breakdown of the samples. And so you can see it's not, none of these are, except for the top left, setosa one is absolutely pure. The others have some impurity. You could have outliers that you would think this would predict are virginica, but actually are versicolor and vice versa. And then below is a plot of the data. And as I was mentioning before, the color coding is for the different species of virus. And these are the kind of stairs we're talking about, the partition of the data. All right, pretty straightforward. And then in the case of regression, a similar concept, except instead of the classification here, you're going to have the value. And in this example from the book, I'm guessing that it's the plain vanilla as we were discussing before. It's an average. And then you can see here the y-hat, the predicted values are plotted again. You've got your partitions, your stairs. It's not smooth and continuous like the actual data. Yeah. So.
And I don't know, you might have already gone over this. I'm sorry, I was just reading that part of the chapter, but is there any kind of rule of thumb as far as Gini scores go, where you just, you want to try, if it's over a certain amount or number, you just want to try a different model that you know
of? That was not covered in the chapter. That's not something
Yeah.
I remember from my learning, but maybe others can comment on it.
Because I know, in the chapter.
Harold, I don't think people kind of talk about trees that way. So for more complex data, your first splits the data, they're not going to do that great of a job. So you're not going to have that much of an improvement in your Gini score. What you hope is that after you've started to subdivide it, eventually you get to a point where you're like, aha, now that I've taken my original 1,000 rows of data and I've kind of broken it up in this particular subset, these 50 rows, if I split it on petal length, I can get a really accurate, almost perfect split between, what I want. And in this other subset over here, where I've got 90 rows, right? Maybe petal length doesn't do a good job for me, but this other feature, color, does an almost perfect job of splitting it, right? And so they don't all have to get split well simultaneously. Some could be a little earlier, some could be a little later. But what you're hoping is that you're gradually, separating out the different classes. So there are other things which I don't know if we'll get into, but as with any algorithm, you're going to look at the metrics to see how well it performs. And so trees are really important because we use them as building blocks. We'll talk more about it next week. But the reality is I use decision trees sometimes to visualize kind of what's going on early in the process, but basically never have I ever had a decision tree be my final best algorithm.
Okay.
Thank you for the question though, Harold.
Yeah.
I have one more piece to add to that. So like Ted was saying, you don't really typically focus that much on the Gini impurity or whatever other splitting metric you're looking at, because you might have a bad impurity at a single split, but it actually leads to better splits later. So it's not super easy to directly infer. Like you might have a first split and it splits your data 60-40 with your target. But then the later splits do much better than that. And so it's kind of hard to infer. And you typically don't look at the Gini score that thoroughly. You look more at the actual metric that you're interested in, the accuracy, the mean squared error, the whatever you're looking at.
Yeah, that makes sense.
Yeah. And I apologize, I skipped over some basic terminology, but you know, you see here how the max depth is set. You know, we'll get to in a second. I mean, this is one of the ways you can regulate. Is that the word? Regulate your tree, prune your tree. Because as we discussed already and previewed already, if you just let it go unrestricted, you just get a way overfit, useless model like this. So, you know, we want to take our nasty, messy, unpruned tree and prune it. Sorry, I'm a dad. Got to throw some dad humor in here. All right, so regulation and pruning. So I guess I apologize. I wasn't able to make the session last time, but I think regulation was discussed maybe in that session or the session before. But the idea is here restricting some parameters to prevent your model from overfitting the data. At least that's how I think of it. And you can see, so on the left side of classification, sort of before and after, and a regression before and after, where you have no restrictions on the model. And you get sort of all this crazy stuff going on in here. Not very clear sort of partitions. And then if you just say, okay, well, keep the number of leaves, or sorry, is this the number of samples in a leaf to 4? Have a minimum of 4. I don't want you to get down to a leaf that has just one data point in it. It turns the partitions into this. So it removes this nonsense going on over here and this stuff going on over here to capture, you know, like one data point. And it generalizes better, I guess is the terminology. And then for regression, you know, here is just basically drawing a line connecting every single dot, except you leave a couple out, and that's no restrictions. Well, that's not helpful as a predictor. That's just repeating the data, really. But here, if you minimize again the number of samples in a leaf, you set the minimum to 10, then you have something that looks more useful. This is not the only parameter you can set. I've definitely played around with that one, and it's useful, especially if you have, I don't know, a smaller data set, I would imagine. But you can restrict the depth. I think that was something, yeah, you've got max depth here. There are others that are not coming to mind. Maybe others can shed light, but what I remember from the classes that I took was like, you get beaten over the head with like, you've got to prune, you've got to prune, you've got to prune, because otherwise you just get out of control overfitting.
So just a quick clarification. There's two broad classes of ways you can regularize a tree. Okay, so one is you restrict how it gets built when it's actually first growing the tree and creating new splits. And so then you can say, hey, don't split when you have less than 4 data points or whatever, and other rules like that. And then technically speaking, pruning is a different approach where you let the tree overfit and then you start snipping away parts of the tree that were built. And so you, gosh, I don't really know how to explain it any simpler, but you build up the tree, and then once the tree is fully built up and you at this point suspect it is overfit, you then go back and sort of say, what is the least useful parts of the tree, and you start removing it. And what's interesting is that when you do pruning, it won't just remove things in the reverse order in which they were added, right? So it's like if the last thing you added was in the lower right corner, the first thing that gets pruned isn't necessarily the thing in the lower right corner. Okay, and that has to do with the fact that the trees are, the algorithm for building the trees just kind of goes like sequentially, level by level. It doesn't, so when you do pruning, you actually do pruning it based on kind of those Gini scores in terms of how much value it added. And so the bottom line is that pruning doesn't always give you the exact same result as limiting the growth of the tree in the first place. And so they are two different approaches.
Oh, so they're technically, okay, I didn't realize they are actually different. Well, this is what happens when you let a newbie do the presentation. Thank you for correcting me.
Yeah, no, it's great. It's good discussion.
Yeah, I mean, for all intents and purposes, to me, it's kind of, it's achieving the same objective in a different way, I guess. So you either prepare, you do like as a prophylactic, or you do it as a cure at the end, I guess. Yeah, and there was some mention of actually, what was it? An algorithm. There are some algorithms that will build the whole tree out and then go and do the pruning. I guess that's behind the scenes. You don't see that happening. Which, yeah. So I don't know which ones those are. I don't know. I guess that's not how CART works. Is anybody an expert?
I don't think pruning was part of the original 1.0 CART, but now we're kind of splitting hairs. I mean, again, you can either restrict how you build it, or you can start snipping away parts that are not all that helpful at the end, and you can do both. So it looks like you have a question, somebody with their hand raised.
Oh, yeah.
No, actually, you just answered. We can do both. Thank you.
Yeah.
I want to add one thing to this. So what they're showing on that left side with no restrictions, you can think of an even more extreme case than that. So imagine that you have a tree, a decision tree that has infinite number of splits. And it just says, okay, everything to the right of -0.5, everything to the left of -0.45. And it just draws about a box around every single individual point. It can perfectly represent your training data, but then when you actually go to do predictions, it's not very useful when it creates just a sort of polka dot pattern where it just draws a box around all of your initial training points. At that point, you might as well be using nearest neighbors or something like that. That's not really useful. So you have to restrict it in some way so the decision tree doesn't just draw a box around all of the points, and it actually does something that's useful when you look at new data. And that's kind of the whole gist here, is there's various different ways that you can prevent that from happening. Because in theory, you just have an infinite depth decision tree, and it just perfectly says when you're at this specific point, mark that as a positive, and when you're at this point, mark it as a false. So that's the idea there.
Right, and generally, I would say this is the linear analogy to what Ryan just said. Like, it's basically just hitting every single point.
I think the only comment I'll make here is really talking about from the reference of your actual data set. So decision tree models are more forgiving in terms of the state of your data. So it can handle data that has missing values. It can handle data that has irrelevant variables, data that has redundant variables. So other models like logistic regression, you have to clean all of that up. Like, you have to do a feature extraction, you have to do a lot of pre-processing before you build your model. Decision trees eliminates a lot of the pre-processing because it can handle, I would say, messy data. Now, one of the downfalls about that is when it builds the tree, if you don't restrict how your tree is going to be built, it'll keep creating branches and keep creating nodes that incorporates a lot of that messiness in your data. So if you don't restrict it and why it keeps growing, it'll incorporate all of that noise. And so when you think of the noise, that's like all the anomalies that, you didn't clean it up. So it's going to create a node and it'll do a split. So and that causes overfitting. So when you're pruning your tree, you're eliminating a lot of that noise, and that helps your model be able to generalize better and make predictions better because you've eliminated and cut all those other branches that lead to all of the noise that's within your data based on like your data set. So in Scikit-Learn, it automatically by default, it has that as none. So there's about 12 different types of adjustments you can make to the parameters to optimize your model. And by default, Scikit-Learn will let your decision tree build all the way out. And it's up to you when you use that technique to then set the criteria for how to prune it.
I was going to pull up the documentation, but that's probably too boring. Yeah, I don't have it cleanly available. Thank you for the comment. Am I back to the right mode here? It kind of looks different on my screen. Okay.
Good.
It looks fine for us, yeah.
Okay, great. Moving on. Okay, so we talked earlier about some of the disadvantages of trees. And essentially one of the things we mentioned was the small changes lead to big problems, or small variations in the data can lead to big changes in the model and the predictor. Wait a second, sorry, I'm now your pictures are all covering my screen, so I'm trying to get back to that other view I had. It's not important. So on the left here, you've got I think they said a 45-degree rotation of the data, which creates a very different partition. Same data set, just rotating it slightly. And whoops. And on the right, let me move this box out of the way. This was, I think what they said was they removed one outlier. It was like a iris with a really wide petal or something, or really long. And the result was to go from this to this. So, the same samples or instances are going to be predicted to be a very, I would think, a different type of iris. And that's just from removing one data point. So this is the problem, but it's I gather, easily solved problem by averaging trees together. And, I think we've all heard of random forests. Many trees, you got a forest. And you take out this and I gather other problems. And I imagine, just like any other models, you can also combine a tree with other types of models in some sort of ensemble to get a better predictive quality without even using a random forest. But that is the subject of the next chapter. And as I said, I think this was just a chapter to, an 11-page chapter to tee up that. And as Ted mentioned, took the words right out of my mouth, it's a building block. A decision tree is a building block. From this conversation and from what little I know, it sounds like nobody actually, except students like me, use these to really predict anything in the real world, or deploy them, implement them. But you kind of have to understand how they work if you want to understand what's going on in a random forest, which is more of a black box model. So this is the part of the whole that you can break down and understand, whereas the random forest, more powerful yet less easy to interpret and really understand why it's doing what it's doing. I kind of got to my conclusion without getting to my conclusion slide, but we've got loads of time left for Q&A. If anybody wants to ask questions of the group, I'm certainly not going to suppose that you would want to ask questions of me. But if anyone wants to take this conversation in any possible direction, we've got 15 minutes.
I can start us off by saying thanks for presenting on this. You did a good job. I think you're a bit hesitant, but you covered all the material. We got through everything. So just talking about kind of the usefulness of decision trees, I would say that they're still actually somewhat useful because you can do more complicated state-of-the-art things, random forests, gradient boosted decision trees, but still very often they're the best way to explain something. So you can solve it with linear regression or logistic regression, like we talked about in previous chapters, or you can do a decision tree, and you can also look at that visualization that you showed on previous slides, and you can actually reason and say, oh, it makes sense because it's splitting on this feature, and then that is leading to this other split. And it's actually very helpful just for understanding a bit about your data and what the interactions are and stuff like that. So I would say that decision trees might not get you the most predictive model, but it's still useful as a tool to sometimes explore your data and understand what's actually inside of it and what is predictive.
I can see that. Would you say that that's even more powerful tool when you don't have a lot of domain expertise in the data set? So like, I've done these exercises with cars. I'm not an expert on cars, but you can figure out that like if it's an automatic transmission versus a manual, it's going to have probably a higher resale price because more people know how to drive automatic. But let's say you're getting into something, I don't know, physics, math. That's clearly I don't follow as well. Like it could really be helpful to break down like, okay, there's something important about this feature because it's breaking it, it's partitioning early here.
Mm-hmm. Yeah, you can definitely look at it and you can say, oh, wow, the first split is some variable, and maybe that's informative to you, and you look at it and you understand, okay, this is actually something that's very important to the target that we're trying to predict. And I would say it's even more powerful in that regard than like linear regression, because linear regression might tell you a coefficient, but you have to look at that in reference to the inputs as well. So just because you see a large coefficient, it might not necessarily mean that it's the most important feature, whereas you can more confidently say that with the decision tree, that maybe the first split is a very predictive one.
I would agree with what Ryan said. I've done this with data sets where you'll first run them through a tree and actually look at that impurity, the purity number, and see how easily it is splitting. If it is just easily splitting, then there's kind of a flag there, And it's telling you, hey, it really does matter if people smoke or not, when I'm looking at lung cancer data or something like that, if they've had a previous history of that.
Yeah, if I could add on to this particular conversation, one thing just to be aware of is that depending on the type of data you have, the number of options for splits can be very different. So if you have continuous data, then there's lots of options because it could pick any floating point number, to split between all of your data points. So if you currently have 1,000 data points, it has 999, assuming the values are unique. It has 999 different splits that it could choose as to where to cut the data. If, however, one of your features is, let's say, you're talking about the weather, so it's, so continuous would be like temperature. And so if one of your other features is cloudy, sunny, rainy, partly cloudy, I don't know, it's got 4 options. There's not that many ways you can split the data when there's only 4 options. And so decision trees will tend to bias towards splitting on continuous data, on data that has more options for how you split it. And so that's just something to be wary of. The other thing I was going to say, actually, I said these in the wrong order, but so what Ryan was talking about is that often when you have a decision tree, most algorithms will output some kind of feature importance scores,
Right.
where it'll, based on which features it used to do the splits, possibly depending on there's different scores, but depending on the score, it generally is based on which features are used the most, if they're used kind of higher up, and if they were very useful, if they actually did a really good job separating versus if they only, did a minor improvement in splitting things, all right? And so that's very useful for seeing like which features are the ones that were most relevant. Like you were saying, if it's something you're not familiar with, you're just exploring it. But I wanted to add the caveat that I said in the reverse order is that, but just know that continuous data is going to tend to always score better than data that has fewer options. And then something that's binary, just 1 or 0, it only has 1 possible split. And so it will tend to score lower. You just need to take it with a little bit of grain of salt.
Are there any other noobs out there like me? This is what Ted is talking about. So this was actually the car thing I was talking about. You're trying to, I think, predict the value of a car on the secondhand market, the used car, and these are the features.
We're still seeing your,
importances.
Glenn, we're still seeing your conclusion slide.
Oh, I see. Okay. Well, thank you.
I think you're referencing something else.
Yeah. I don't know. I don't know how to use this.
You probably need to stop sharing and then reshare if you're not sharing your whole desktop. I don't know if it's worth it.
It's not all that important, but yeah, I wasn't sharing my entire screen. That was the problem. But yeah, so here's just an example. I think you can see what Ted was talking about. Maybe it's small, make it larger, but this was for, some car data. And the age, no surprise, and the mileage or kilometerage were the most important features. Like that's intuitive, right? But you're buying a car, you want a newer model, lower mileage, it's going to be more valuable. Those are the biggest predictors. But say you're not dealing with cars, you're dealing with something that you're not as familiar with, this is going to be very helpful.
Yeah, and so my point was, if you looked on there was a feature, it was like maybe 6th or 7th, and it was like number of doors, or is it a sporty car? And those have very few options. So just know that doors and sport model, no, they shouldn't actually be the top feature, but maybe they might be a little bit higher than where they look. If they're like 6th or 7th on the list, maybe they could be 5th or 4th. But they're just a little bit, I don't know what the right word is, but they might rate lower just because this algorithm tends to prefer continuous data.
And I have a weird question, but does it really matter whether or not there's a close relationship between the age of a vehicle and the miles per gallon?
I think you're predicting price here, right, Glenn?
Yeah, it was to predict price, yeah. And sorry, when I said mileage, I didn't mean miles per gallon, like fuel efficiency. I meant actual how many miles are on the car. Yeah.
Yeah. I don't know where my brain went for that.
Yeah, it's okay. And these would probably be very highly correlated, right? I mean, there is the old expression, it's not the age, it's the mileage. That's what I say about my knees all the time. But most of the time, you have an older car, you have more mileage. Anyway.
Well, the other thing that's interesting in this data is this is obviously European data because
Right.
In the US, we don't care about tow bars, and that's what their number 6
Right.
criteria. But
Right.
they trailer everything in Europe. They don't have Ford F-150s in every driveway like we do. So, they have to go and get, rent a little thing at IKEA to haul, a little trailer to haul their thing back. So you need a tow bar. So
Right. Good point.
That's
Thank
funny. I didn't know that.
Just
All right.
to clarify something here about the feature importance, because that wasn't mentioned in the book. Is that a feature of the card algorithm, or is that computed using another algorithm? How?
It's pretty much it's part of the algorithm. Almost every tree algorithm will give you options for different kinds of importance scores, and it's based on just the tree itself.
Right.
Yeah,
I
when
mean,
you're
the naive approach would be to looking at how the tree is generated, right?
Yeah. So what features are used most often in splits, highest up in splits, and how helpful each split was. That's generally the criteria that goes into the score.
Yeah, when
Okay.
you're looking at a decision tree, the root node is the most predominant feature that, and then it kind of goes down like a hierarchical. So if you're just looking at a decision tree, that root node is the most predominant or most important feature in the data set. And I think the only thing I would add is that I do use decision trees in quite a few different ways. I do use it more like an exploratory data analysis technique. So I use it sometimes to maybe kick off a large scale project, or oftentimes, like there's certain projects where you might want to go with a more complex model, but then if someone's like, okay, what can you give me in like an hour? um, just let me know, because you'll have a lot of projects like that where some stakeholders will say, what's a good enough model? We just kind of need this for such and such. What do you have? What can you give me in 30 minutes? A lot of statistical software applications have decision tree models. So it is always a good go-to for a good enough model. I do like to use it for feature extraction after I have deployed like an unsupervised machine learning model. So I know like we're going to cover like k-means clustering in a couple weeks, but when you do that model, I then like to do a decision tree model on top of that data to kind of understand what features are more important and why that model classified the data. But I do use it just as exploratory, and then it might kick off a more larger, more complex model. Another factor as well is that sometimes when you're doing data science work, the more complex model is not always the one that you use. And this is where the book mentioned like the difference between white box models and black box models. A lot of times, like the simple models like linear regression, logistic regression, decision tree models, sometimes they might be preferred over like a more complex model like XGBoost or something like that, just because of its explainability. And the stakeholders, if it's like a stakeholder that doesn't really understand data science and they just kind of want a just enough model, you tend to kind of use some of those models. And in that instance, if I have to use more of a classical model like decision trees, then that's when I really do work a lot of the parameters. So I know the model's going to overfit. And one of the things that the book didn't talk about, but I kind of mentioned earlier, when you're building that model out in Scikit-Learn, you've got about 12 different parameters you can adjust. So things like the splitter parameter, the maximum depth, the min sample split, the min sample leaf, and the maximum features, those are 4 parameters that you can work with that will help your model generate higher predictive accuracy results if you have to use it.
Thanks, Christy. All right, so Glenn, I'm going to echo what Ryan said. I think you did a nice job. You covered all the material, and that's all that we ask for. We don't ask the discussion leaders to necessarily have to be the super expert in the field. We're just covering the different topics so that we can have a discussion. So thanks again for doing that.
I looked at myself as like a moderator.
Yeah,
Not very
exactly.
well informed moderator, but a moderator.
All right, so I wanted to just cover one topic leading up to next week. I don't think this is really discussed in the book when it talks about ensemble models, but I might have missed it because I haven't read that chapter in super detail. But Maya showed us this picture, I think, last week. And so this talks about bias versus variance. And of course, in a perfect world, we'd love low bias, low variance, but tends to be that we have algorithms that are either low variance, but unfortunately might have high bias, or that are high variance and low bias, okay? And so something like a decision tree, okay, tends to be in this quadrant, okay? It's low bias, high variance. And something like simple, like a linear regression, tends to be in this quadrant, where it is low variance, but it could be high bias. And so if people have trouble sort of remembering, well, what's bias, what's variance, if you can remember the picture, that's great. The way I think of it is, you know, if you have a biased view of the world, then you're likely to wind up off center on the target. So for example, a linear regression thinks every relationship in the world is a line. Not every relationship in the world is a line. Some of them are curves. So let's just say, for example, that the price of a home relative to its square footage is quadratic, okay? So that it's not just a multiple of the square foot, but when you have a really big house, there's a premium associated with it. And so you're actually paying more per square foot. You're not just paying the same, you know, whatever, $100 per square foot. So in that kind of a model, a linear regression is going to always underpredict the price of really big homes. And so it's going to miss the mark. And no matter how many different ways you build the linear regression, it's always, even if you use different data, different cities, it's always going to consistently miss the mark, and it's going to underpredict the price of expensive homes. If you build a decision tree, well, then you may get this overfitting problem, and you may have, you know, individual predictions that are kind of overfit and are off the mark. But on average, it can fit to anything. Okay, the decision tree's view of the world is I'm going to divide up the world into little rectangular patches. And so anything can be divided into rectangular patches. And so that view is not biased. That's why we say it's low bias. And so as a lead in to next week, when we start talking about ensembles, you could say, well, what if I built a bunch of different decision trees, let's say with different sets of data or subsets of my data, different cities. And I, like Glenn said, I kind of averaged those results together. You can see that maybe what you would tend to do is you would tend to get an average that's kind of right in the middle, and that you might, you know, this was a question a couple decades ago. Could you actually take a collection of weak learners that aren't that perfect, that aren't in this upper left corner, and could somehow combining the information from a collection of weak learners give you a strong learner that's in this upper left corner? And so ensembling is really about, do you gain anything by collecting things together? And in some cases, you might collect things together and end up no better off. But what people sought out and have successfully done is find ways to collect smaller, weaker models in ways that actually improve the overall results. So I hope that's useful. I hope that's an interesting, a helpful segue going into next week.
Can I ask a follow-up question, a really quick one?
Yeah, sure, George.
So for regression, how popular are tree-based models for regression? Because they have this piecewise linear, you know, approximation if you look at graphs. But I'm just curious how useful or how used they are in practice for regression problems.
I don't know. Anybody want to comment on that?
I would say that for state of the art, they're very common. If we're just talking about decision trees, they're very common. And then if you go a layer deeper, random forests and gradient boosted decision trees, they're very, very common. It doesn't really make a difference if you're doing classification or regression. They're equally good for both. It's a slightly different underlying algorithm, but it's still very, very predictive.
Right. Got it. Thank you.
Anyone else?
I can
Just
talk about
one-
NP complete if people want to hear to listen to it. What it is.
All right, well, why don't we formally end today's session, and we'll stop the recording here for posterity.